On behalf of NCCRD, I welcome Professor Ramesh from IISc Bangalore. Professor Ramesh completed his PhD from IISc Bangalore. He is now professor in Aerospace Department in IISc Bangalore. His area of expertise are aerodynamics, turbulence, vortex dynamics. He has performed exhaustive measurements in wall shear flows, especially in sink flow boundary layers with strong pressure gradient. And he has several JFMs based on these strong pressure gradient boundary layer flows. And he'll be now taking over the session. I'll be presenting as the wall shear turbulence and its measurements. Thank you.
Thank you very much, Dee. Thanks first of all for welcoming me to this meeting. So let me try to, I don't have a clock, so I'll probably keep this somewhere. Let me try to take you through wall shear turbulence and its measurement, because the moment you go for wall bounded flows, it presents peculiar problems, because the fact that unlike free shear flows, there is no bounding wall. Even conceptually, a wall bounded flow is quite complicated, because the wall can do all kinds of things. It's not just a no slip boundary, but it also can do all kinds of other things, even for turbulence. So there are some peculiar things which happen in a wall bounded flow which you never get to see in a wall free flow, like a jet or a wake or a mixing layer. So I will be talking about two different kinds of wall bounded flows here. One is the traditional boundary layer. The other one is what is known as a wall jet. A wall jet is interesting because it's, while you might probably have come across the idea of a boundary layer, all right, a wall jet is a marriage of a jet and a boundary layer. It has aspects of both a jet as well as a boundary layer, and it's some very rich physics embodied there. And then also these present challenging, they present challenges in terms of measurement too. So I'll talk about these. First, let's talk about some broad ideas of turbulence, and then move on to measurements with Hotwire Anemometer. Okay. First of all, the people who helped me with this, this is my former student, Shivsai Dikshit, who is a scientist at the Metrology Institute at Pune. He has done lots and lots of measurements in boundary layers, and is now making atmospheric boundary layer measurements, planning some large atmospheric boundary layer measurements in the country. The other student who worked with me earlier was this Damodaran, was a master student with me. He measured this for his semi thesis on wall jets. Again, I will see both these. So let's start with some aspects of turbulence first. It's going to be a rapid fire kind of discussion on turbulence. So I will not go through the details beyond. Anyway, you have had a great elaborate kind of discussion the morning on turbulence. So let's get down to business. Okay, now this is probably the only slide. I pulled it out from all the old slides, so I'm sorry I could not get some of the movies here on the screen. If I had a movie, I would have preferred that to this. Well, this is the only one where you will see the equation. This is just the boundary layer equation as applied to a Reynolds decomposition as applied to a boundary layer. So what you do is really write the velocities like u as a mean plus fluctuations, the AC and DC components. Likewise pressure. So if you plug it into the governing equation, which is your Reynolds, this is the Reynolds average Navier-Stokes equation, you of course all the overbought quantities here are the capital quantities which are interchangeably used, or all used for the time average quantities, and the prime quantities you see there are used for the turbulence fluctuations. So essentially you break it into this form. Typically it is this, the extra term there, over and above the molecular diffusion. This is the extra effect because of the so-called Reynolds stress, which is actually a virtual stress. You must remember that. It is not a stress in the sense it's a real stress. Remember, it has come from the left-hand side acceleration terms. For that reason, it's called a virtual stress. While at it, I'll make it a point. This is, you see why correlations are important. You heard in the morning about cross correlations. Right here you see the need for that, right? There's u prime, v prime. I need to be able to measure the velocity component in the streamwise direction and the normal direction simultaneously to be able to come up with this correlation. It's a correlated quantity. And of course, this minus u prime v prime is the major player as far as turbulence is concerned, especially for momentum transfer and so on. So typically, you can model this, of course, in this fashion with some sort of eddy viscosity or diffusivity here, kinematic diffusivity into the mean velocity gradient, pretty much like what you would do for a laminar flow. Now, typically, this nu T by nu is of the order of about 25, 30, depending on the Reynolds number. So what it really says is the diffusivity because of turbulence is a lot larger than what you would have from the molecular diffusivity. That's the moral of the story. Okay, now first of all, what is turbulence? So let's look at a typical, the mean velocity picture. If you look at a laminar flow, what you see here is the mean velocity profile on the laminar flow profiles. This is the distance from the wall on this axis. On this axis, you have the mean velocity plotted. So typically, you see this kind of a velocity profile in a laminar flow. You're talking about flow over a flat plate, for instance. A boundary layer formed as a result of that. You can very clearly see this variation of velocity till you reach the free stream. In the case of turbulent flow, it's a lot fuller as compared to that. You see here, it's less full, whereas here it's a lot fuller. On an average, instantaneously, of course, what would you see? If you look at a turbulent flow, this is like a time average frozen picture, so to speak, in time. This is how it will look like, average picture. And as Professor T.S. was mentioning in the morning, you can see that this region is almost like an inviscid flow profile, except the region close to the wall where you have sharp gradients. And in fact, if you try to model it with a kind of simple-minded velocity profile, this is what you would try first of all. You would say, well, I'll model, this should be a capital U, the top, that's also the mean velocity, divided by the velocity in the free stream. The local mean velocity divided by the capital, I'm sorry, it should not be small, it should be capital. Because I said that I'm using capital quantities for the mean flow. So if you now normalize in this fashion, you expect it to be a power law like this, where y is the distance to the wall, and delta is the boundary layer thickness, and n is typically a fractional power of the order of 1/7 of that order. But the trouble, however, is that this velocity profile is not good enough for many practical things. For instance, why would you be interested in these descriptions at all? You would want to be able to find out the shear stress at the wall, if I want to know the drag, right? Or heat transfer, for instance. For considerations like that, you are interested in the slope at the wall. If I try doing the slope at the wall with this, clearly I have a problem. There will be a singularity. So this is not good enough. That's how people started looking at a different description of the mean velocity. They said this power law description is going to be misleading, mainly because it fails to take into account the two-layer description. You see, there is a region where there is a slow change here in velocity. The mean vorticity, so to speak, is very less, whereas here it's very strong. So idea is, somehow if I can zoom into this region by some trick, I can see that in great detail and address that point. That's really what we're going to do now. So what did people do typically for that? Traditionally, well, they had this description called the log law, right? So maybe I'll go to that slide. Where they said is, they divided the flow into what is known as an inner region and an outer region. So the region here, you can call it as the inner region roughly, is the outer region. And they said the region close to the wall is going to depend on the velocity, mean velocity is going to depend on things like viscosity, density, and so on. So if you write the dimensional relation, the mean velocity in the inner region, you can write it as a function of y, shear stress at the wall, because that's what is driving the boundary layer in the first place, viscosity and density. And you can non-dimensionally write it in this fashion. The outer region, you can write it the same way here. Y, again tau wall is important because if there is no tau wall, there is no boundary layer. That's also an important parameter. Rho, delta, u infinity. Now what is interesting about this is not so much what is contained here, what is not contained here. You find that what is conspicuous by its absence is viscosity. So the idea is that the outer region is relatively free of viscous effects. That's the expectation. That's of course consistent with what we saw. We saw that the gradients in the outer region were a lot weaker than what you have in the inner region. So you could in fact write in the so-called defect velocity formulation, and that is essentially velocity, mean velocity, any location in the outer region, minus, again I am sorry about the inconsistent use of symbol, this should be the free stream velocity. The difference in velocity is what matters here, divided by the so-called friction velocity. Friction velocity is simply the shear stress divided by rho, square root of that. You could write in this fashion. I see some of you might have heard this, I think in one of the last year in mechanical department, this informal course when I did. I told you about a very interesting story how this was done. I don't know how many of you remember that. It's about Corman, how he wrote this on supposed to be on the wall of a train and so on. It's a very colorful story, but maybe for some other occasion we'll see. The bottom line is that you have an inner layer with this description, an outer layer which has a different description. The expectation is that there's a region over which both these are simultaneously true. That expectation leads us to the so-called overlap region, this kind of a velocity profile. U normalized by the friction velocity equals 1 upon kappa. Kappa is the so-called Corman constant, which was believed to be a universal constant, not anymore. Okay? Recent years people have proved that it's not universal, and then including some of our own work has gone towards making that point that it's non-universal. And a logarithm of y normalized in this fashion plus some concept. This is really the intercept on the axis. We'll see what it is graphically. So if you look at that, this plots in a semi-log plot, first of all. Remember, because the logarithmic relation, if you plot it in a semi-logarithmic plot, it will show up as a linear variation. That's really what we are doing here. What do you see here? This axis is what is known as the y plus or yu star or yu tau by nu. Okay? U tau, u star, these are interchangeably used for the velocity scale based on the wall shear stress. And this axis is u by u tau, u by u star, which is really normalized velocity, which is also called as u plus in some literature. You plot that, you see it as a typical variation like this. Look at this region. It's a nice linear bit which indicates there's indeed a very nice logarithmic variation. This is of course one of those celebrated results in turbulent boundary layers, or pipe flows for the matter. In fact, there are not that many great results, nice, neat results in turbulence literature. I would say this is one so celebrated that it's this Corman constant is thought to be, as I said, universal, which is not anymore. The other celebrated result in turbulence is what you heard about in the morning. Kolmogov's celebrated result was spectrum. And interestingly, I don't know if you realize that the Kolmogov result also is actually, the derivation goes like what I said here. You divide this into just as you divide it in the inner region and the outer region, and you expect there's a region where there is a overlap of these two behavior. We'll see that later. Kolmogov also goes about. The key point about the log region is that note that in this region the viscous effects are negligible. It's inviscid, in other words. That's the beauty of that. So it appears that all the viscous effects are first order confined to the region near the wall in a boundary layer. Okay, so let's now look at a typical boundary layer, a slice of that. There's an instantaneous picture, flow visualization. Could be smoke, dye, or whatever, depending on which fluid it is. You do see this sort of random motion, and what you see primarily are these kind of organizations, okay, where there's a large scale. You talk about turbulence can be often thought of as a tangle of vortex lines. It's the interplay of all these, what you call as eddies. Now this eddy is one of those words which is used loosely. Everyone seems to be using, without precisely defining, but everyone seems to know about what it exactly means. Broadly speaking, it's a circulatory region of activity flow. But you can make it more precise by ideas like this correlation, which Professor T.S. mentioned in the morning. So you can now talk about an eddy which is as large as this, a large eddy for instance. Whereas I could talk about a small region here, there is this variation. You can talk about a relatively smaller eddy, which is, you can see very many of those, right? Okay, so it's all about this interplay of these eddies. Okay, so you can talk about these as parcels or localized regions of vorticity which talk to each other through the interplay of this is what gives you the velocity field. Right. Now, if unfortunately this is a picture I wanted to show you and a beautiful animation. If I could run that, what it would have shown is that there's a region inside the boundary layer. It's very dynamic. You'll see that moving in all kinds of crazy fashion, both spatially and temporally. That's of course the essence of turbulence. But yeah, a streak here in the outer region is outside the boundary layer. It would of course meander like this, but it's a lot more ordered. It is not as confused or random as this. So that brings us to the point about randomness. What is turbulence? Well, broadly you can look at it as a region. Turbulence is, is a state of flow which you can have, I can list it here, 3 characteristics. You can say random, you can say 3-dimensional, a third is it's vertical or rotational. Okay, but then you could actually, this is only broad operational definition, you must remember. This is very important of course, it has to be vertical. Okay, it's in other words it should have vorticity. There's no vorticity, it's not turbulence. 3D, it's a 3-dimensional motion in general. That's what the so-called vortex stretching phenomenon, for stretching a tilting phenomenon, is a 3-dimensional phenomenon. That's what is responsible for the so-called cascade of turbulence, which transfers energy from the large to small scales. But having said that, there's such a thing called 2D turbulence too. Okay, that's there in atmospheric flows and so on, where some anomalous behavior happens. We will not concern ourselves with that. In atmospheric flows also, sometimes people talk about 2D flows. We will not talk about it here. Or the other classic example of 2D turbulence is when you have a soap film, you can have flow in a soap film. The turbulence that organizes in the form of a 2-dimensional turbulence. The other classic example is of course when you talk about the pattern and the gas pattern and what is that planet? The rings of Jupiter, right? That is supposed to be 2D turbulence. Some people believe it's 2D turbulence, but we will not concern ourselves with that. So we will, our operational definition, use it as 3D and vertical. But what about is the random bit? What is random? Random is something which you can use the other word is stochastic. I cannot, as against deterministic. Now what is the precise definition of deterministic? Deterministic means if I know the present, somehow I should be able to know the future if I know that it's deterministic, right? Now you may say, going by that statement, turbulence also should be deterministic because I have Navier-Stokes equation or Newton's law. In Newton's law, if I know the state now, in principle I can evolve to the next state by integrating it forward in time. So what exactly random means? Let's see. This is where the idea of autocorrelation is very useful. In fact, you can use it as a definition of randomness. You take this signal like this, you take any time series ut into ut plus tau, normalize it in some fashion like u square t. Over bar refers averaging, right? You take a signal u of t and stagger it, offset it with this tau time delay and take the product and take the average. This average is a long time average typically, so you have a, this is the proper, this is the definition of an average. Remember, this average makes sense only if it is what is known as stationary turbulence. Okay. The key point about this is that if I now plot this quantity, let's call it as r tau, which is tau is the time delay, right? If I plot on this axis tau, the time delay, and plot this r tau here, this takes a value of 1, I'm sorry. Whereas typically it goes like the typical turbulent flow, it could look like this. Now physically what does it mean? It means, physically what does this say? If I'm here, somewhere here, I make tau equals 0, right? That's this point. That means I'm trying to see statistically how well my signal, the present is connected with the future. What this says is, if this is the present, this is the future which is tau away from the present, how well it's connected in an average sense. What it says is, the present is connected to itself completely. That's no surprise because you are If we make tau equals 0, you're comparing the same signal. But with future, how well is it correlated? If you find for a reason that your R tau becomes like this, right? It's 1 only when tau equals 0, elsewhere it's 0. That means the present is only connected with the present. No connection at all with the future. That's in fact the definition of a random signal. Random means the present is not at all connected with the future. Whereas turbulence is not completely random, because the present has some connection with the future. You can do the same thing for space also. How well this point is connected with the other point statistically, right? After all, it's a fluctuation in both time and space, right? But then it's no surprise again, because you know there is an eddy which is as big as this. This point, they're going to be connected. They are talking to each other. It's well connected to that. So, which means turbulence is not completely random. Having said that, we can use, as far as the data processing is concerned, all the tools of random data analysis, which is all well developed in communications, electrical engineering, and so on, very effectively for turbulence, right? All those ideas which evolved in terms of the so-called, one of the very powerful techniques in turbulence research is, any time series research in fact, is the so-called FFT, is a remarkable invention, I would say, the fast Fourier transform algorithms, without which you cannot do many things now in experiments. That's all mainly developed in the context of a random thing, which works just as well here. But remember, turbulence is strictly at a conceptual level, not random. It's only seemingly random. Okay. All right. So let me, as I said, I cannot quite run this. So this is how the flow inside will look. We look at the inner flow. It almost like a placid. It's not as disturbed as outer flow. Certainly, it looks a lot more quiet. Okay. These are different pictures, and again, as I said, I'm sorry, I'm replacing my movie with all these pictures. The typical flow will, you can see that it's getting all jumbled up. A nice parcel of fluid is getting strained and so on, rotated. So it says there is a lot of strain rate as well as rotation. That's what this is demonstrating. Okay. Now we come to the idea of spectrum. Now what is this spectrum? This is another, when you talk about any fluctuating field, we are interested in finding out what is the frequency content of that. Now this goes back to the work of, remarkable work of Taylor, G.A. Taylor, who wrote a landmark paper in the 35, who started with this analogy. If you take a prism and send white light through the prism, it's broken up into the constituent colors. Likewise, if you take a turbulent signal, fluctuation, and send it through this prism called Fourier transform, out comes the spectrum. It tells you which frequency has how much energy. This is a measure of power actually. This is power spectral density. And what is plotted here in this axis is the so-called wave number. This is, by the way, spatial spectrum. You're talking about what happens in space. So, for example, you could ask yourself, an eddy which is, for example, if you have an eddy as large as this, you could consider, take 2 points like this, right? And you can talk about a length scale associated with that. The inverse of the length scale is the so-called wave number, which is what is plotted here. What it would say is that, for the matter, if you take a length scale of this, inverse of this, the k, how much energy, kinetic energy, is contained in a typical length scale like this. So the proportion of energy contained in very many scales is plotted, and you can see that if you integrate the area under this curve, that will give you the total kinetic energy at that location. Okay? This is a broad idea. I can do the same thing in space and time also. That's easier because you put a probe at a given location, right? It changes with time. So if I want to remember, this axis here is the wave number, inverse of a length scale, which means to be able to get that, I should get a space series. A series in space. So, for example, if I have a time series, a space series like this, where this axis could be something like x, and this could be u. So if I do the Fourier transform, I'll get something like this. Whereas if I do this in time, so that again a spectrum like this, a signal like this, this would lead to a spectrum involving k, the inverse of wavelength, whereas this would give me a spectrum, temporal spectrum involving frequency or omega. Okay. Now, how do I get something like this? I could take an instantaneous picture of the flow with a PIV, for instance, particle image velocimetry, which in one shot will give me the velocity at different points in space. It doesn't give me any variation with time, of course. I'm talking about typical conventional low speed PIV, right? The typical 15 hertz kind of traditional PIVs. There are also what are known as the high speed PIVs. They are not that great in terms of, they are not yet very large in terms of temporal resolution as yet. You can go up to 1000 hertz or so. Anyway, so I can get this like a instantaneous shot from a PIV and construct this kind of picture immediately in principle. But you are only limited by your interrogation volume in space and so on. That's the usual thing with power of the PIV laser and so on. So whereas here, if you want this, traditionally this was what is done, is it uses the Hotwire Anemometry, for instance. It gives me the time history of this at a given point, a point measurement, as PIV is a global measurement. So what this shows is that there's a region here, this is so-called, what first of all it says is that more energy is contained at the largest scales. So now inverse of the length scale would be k. So the k value low means is a the length scale is large, 1 upon k. This is like length of the eddy would be 1 upon k. This axis k, 1 upon k will give me that. So you're talking about large eddies here, small eddies here. And there is a cascade, so to speak, of eddies, larger eddies passing on the energy to smaller eddies and so on, which we heard about in the morning. Okay, and this is how through the so-called cascade process, energy is transferred. I will not get into the details. Now, this region of the flow is the so-called energy containing range, depending on whether you are in a shear flow, turbulent boundary layer, or a jet or a wake or whatever. Depending on that, this depends on the boundary conditions of your problem. So the idea is that broadly speaking, you have, this is how turbulence shear flow is all. Why is it called a shear flow? Because you can imagine broadly the cartoon like this. You have UV, du, dy, the production, dominant terms in production. Du, dy is of course about the mean flow. This UV refers to the Reynolds shear stress, as it's called, of the large eddies. So you can say that the large, relatively large eddies I indicate in this fashion. This is x and y. It's typically aligned in this fashion, and typically you will find it's aligned along the principal axis of strain of the mean flow. The mean flow u of y, you can in principle calculate what is the principal axis of strain, the usual fluid dynamics assignment problems. So it aligns itself in the direction of that and extracts energy through a term like this. And it passes on that energy to smaller and smaller eddies. That's how so the larger eddy is one which gains this energy from the mean flow and passes it on to smaller scales. Now what's interesting thing is that the larger eddies have relatively longer time scale, right? Because they are long, for it to even do a circulatory activity, crudely speaking, would take longer time. As the length scale becomes smaller progressively, as you go down this, the time scales and length scale all become shorter till you reach what is known as the Kolmogorov scale somewhere here. The Kolmogorov scale is the smallest scale possible, right? Where typically you can work it out by simple dimensional arguments. So at that scale, if you call the velocity scale as v of k and length scale is eta, if I construct now a Reynolds number based on that, that will be 1. What does it mean? It's as viscous as it gets. Your Reynolds number is very, very small. Reynolds number is small means viscous force is overwhelming. So remember, I started by saying at the large eddy level, away, especially away from the wall, turbulence is in the physical space, turbulence is almost inviscid in the outer portion. And that's clearly the case here also, where you see this part of the eddy, it's very inviscid. and as you go down towards this Kolmogorov scale, it's viscous. It has to be viscous finally because it's a viscous dissipation which transfers as demanded by second law of thermodynamics into the heat sink. All the energy goes to the heat sink. That shows up as dissipation. Now the key thing is that there is this very interesting region here where the eddies here become, or the fluctuating activity becomes independent of what happened here. That's what T is referred to as the forgetting the large scale conditions and so on in the morning. So what happens in that case is that there is a very interesting relation. Okay, so we have, I told you earlier, the mean velocity description, you can break it into an outer region and inner region, right? So outer region which is inviscid, the inner region which is viscous, very close to the wall. There's a region where you expect it to be a overlap which is partakes of the nature of both these regions. Likewise, here there is this outer region, this is like the outer region where it's all inviscid, the larger eddies, whereas here these are smaller eddies which are as viscous as they get. The expectation is that there is a range of intermediate eddies which have a similar behavior in the spectral space, right? So for that region, if you now write this is a celebrated result of Kolmogorov. I'll show you if I can, it's not moving. Okay, so this is the last slide on turbulence, by the way. So the energy spectrum, E of k I'm called. So if I write it as E of k, dimensionally it will have the form. Remember, E of k dk, if I take E of k dk and integrate it over 0 to whatever is the maximum value, that would be the kinetic energy, right? So clearly dk as a length scale of 1 upon length. So this should be kinetic energy by L, okay? Kinetic energy into L. So that this will be of the dimensions of this will be U square into a length scale because this is 1 upon length scale. So it becomes a kinetic energy, specific kinetic energy. There is no M here, right? Oops. So, so that's the reason why I have written this E of k equals Vk square. Remember, we are going towards that end of that. The velocity typically you expect it to scale like the Kolmogorov velocity scale square because it has to have velocity square into a length scale into a functional form of which is obviously going to be the independent variable here is k, the wave number, which is non-dimensionalized by the Kolmogorov length scale. So how does it proceed now? You substitute for Vk, which you know from Kolmogorov, purely by dimensional arguments. It has to be, this can only depend on the so-called dissipation, specific dissipation, and kinematic viscosity. Likewise, this is a Kolmogorov length scale, right? We substitute all these into this, and for the f of k eta, you take it to be a power law form, which is k multiplied by eta power n. That's what Kolmogorov did. And he rewrote that now. He combined all those viscous terms there. If you combine all the viscous terms, it takes this form. He found out when those viscous terms, the power, the index goes to 0. That corresponds to minus 5/3. Okay, so the region where we saw in the last slide, where the power law, the intermediate region is independent of viscosity and is also isotropic. The eddies become, remember the large eddies are not isotropic because there's a shear. The eddies have to orient themselves along this region to be able to extract maximum energy. They have to toe the line of the mean flow. Whereas the small eddies don't care. They are only interested in getting the energy from the large eddy, but they don't have any preferred direction. Under those conditions, you'll get this nice 5/3 minus 5/3 power. That's called the inertial subrange. This is the dissipation range, and this is of course the so-called energy containing range. Now I must tell you something very peculiar about boundary layer turbulence. This is, of course, this region is universal, no matter what the flow is. Okay. Whereas in the case of boundary layers and so on, or wakes or jets, this region could be different. For instance, one of the it's almost a subculture in boundary layers. There is a region here which is known to go like k to the minus 1. Not in this region, away closer to this large eddy region, right? Where it goes like k to the minus 1. You don't see that in the case of jets or whatever, other flows. Now this k to the minus 1 is in fact a very controversial topic in the literature, I must tell you, which is some people are saying you have to go to very high Reynolds number very elusive, okay. But anyway, that is something is peculiar to boundary layers. All right, I will not say anything more on that. Let's now move on to Hotwire Anemometry. So this is all I'm going to say about turbulence. So whatever I said so far. So let's now talk about Hotwire Anemometry. So what is the essential idea? So you have already seen that you have a thin heated wire, which when there's a flow, obviously it's heated, and there's a flow past that. There is of course heat transfer to that, loss to that. As a result, you have of course all this circuitry which does whatever. We'll come to that in a minute. And the heat transfer is proportional to the velocity, which is obviously responsible for that heat transfer in the first place. So typically, you can write this relation non-dimensionally as a Nusselt number, which is of course the main quantity here, which is a function of Reynolds number. And of course, what is this? This T wire, temperature of the wire. This is the temperature of the medium, right? This is the temperature ratio or the overhead ratio. Now you could rearrange this in this fashion, and we'll see that in a minute. But I must tell you, more complicated functions are possible. If I operate at very low velocities, for instance, let's say there's a wire, hot wire. The velocity past that is not very large, let's say. What would happen is that there would be natural convection effects, in which case this functional dependence will also have a Grashof number coming into picture there, right? And in fact, some people would say if the velocity is very low, of the order of a meter per second or so, you cannot quite use the hot wire because the Grashof number effects will take it away from the so-called King's law, which we'll probably may have occasion to see later. Okay, so a typical relation goes like this. It's 0.39, and this is the Reynolds number to the 0.5. Some people would use even things like 0.45 or so as a fit. Okay, now whereas as T.S. said in the morning, you could derive this relation from simple heat transfer arguments, assuming the Nusselt number relation for if you do the forced convection problem for a flow over a circular cylinder. That's the sort of thing you'll get. Now you can of course write this as I square R. After all, this is a Joule heating, right? There is the wire being heated up, which is I square R, which is non-dimensionalized by this conduction. This of course is the Reynolds number. So if you now cast it in a different form, you write it as absorb all these things, parameters into this, write this so-called King's law, where E square equals A plus B rho Q. Now what you do is, you go to a known flow, that's where you do the calibration, right? And then measure that independently, the velocity independently. And then you can also measure the voltage. You put a hot wire into the same flow, get the voltage, you can tabulate it, and find these constants by any of the methods. I will not go into the details of that. The moment you have these constants, we are in business. But that's easier said than done, I must say, because I must tell you right away, Hotwire is a very whimsical instrument. It is a mind of its own. Be warned. Don't take the Hotwire for granted, right? Despite using Hotwire for almost decades now, almost 60, 70 years, people would say, though we use that, it's more of an art than a science at some level, because it's very whimsical. So there are many practical dirty tricks if you are going to be using that. For instance, I always tell my students, they are making measurements with Hotwire, don't switch it off for heaven's sake. There will be calibration drifts and so on. Whereas if you keep it on for a long time, it turns out that the behavior could be very good sometimes, and many people have found this. There are many tricks like that, okay? So Hotwire, there are things like calibration drift and all that. I can probably, if there is time, I can tell you about some of the things we have battled with Hotwire and so on. We have also built our own Hotwires and so on, and I must tell you, it's absolutely whimsical. But that's the best we have for time solved measurements, right? Okay, so if I have occasion, I'll tell you more of that. So typical Hotwire probes will look like this. This shows, of course, I'm not basing it on DISA or Dantec or anything, okay? We make our own Hotwires, okay? Even we get our even source our own tungsten, everything is, the only thing we buy outside is what is known as the platinum. I'll come to that in a minute, this sensor, right? Most of these we make there in-house, or someone makes it for us. The different, so you may not see the standard DISA things here. in terms of all descriptions, in terms of size and so on. Okay, right. So a single Hotwire is all exaggerated. The prongs are exaggerated. You can see that what is done here is not the tungsten wire you heard about in the morning, where it's a tungsten wire, you directly heat it, you are in business. Typically tungsten wires are the order of 5 micron, that's your sensor. We use what is known as a Wollaston wire. It's platinum coated with silver coating, platinum rhodium alloy coated with silver, where there is a central region where you etch it out by an electrolysis process and expose that. You can see that here. And it is this active part of your sensor. So it is this part, when the flow goes over that, it will respond. The advantage here is that I can have a fine control of my L, the active length of the wire. We will see that while this is the full length of the wire, is the active length which is going to play a major role. We will see why it is so important when you choose a sensor, right? Okay, this is of course a single wire probe. This is a so-called crosswire probe in the form of an X. So you have 2 probes like this, two sensors like this at 45 degree each, right? Typically 45, it could be other angles too. So what it would measure, of course, is if I have a probe like this. So if I have a flow which comes like this, what matters is this component and this normal to that, right? So one of that will measure something like U plus V by root 2. The angle I'm taking to be 45. Sine or cos 45 is 1 by root 2, right? So the other sensor will measure this U minus V root 2 as a function of time. Simultaneously you can measure both. When you measure both, I can in fact, if I add this, I'll get U of t, subtract that, I'll get V of t, and so on. And if I take the product of that and average, I'll get UV. That's it. That's how it is done. Rest are details, right? Okay. Now, there are many variants of that. This probably is something very peculiar to measuring. Shear stress is a nightmare. What is used traditionally is what is known as a hot film, right? Shear stress or heat transfer, they are closely related. Okay. So a simple version of Hotwire itself, if you know the behavior of the so-called viscous sublayer close to the wall, I can use it close to the wall and measure the shear stress. I will not go into the details here. If you want, it's there in one of the papers. I think one of our papers, I can give you the reference. This is called a surface Hotwire probe to measure wall shear stress. Okay. Now we can have, if you want to measure all the 3 components, you can have also a triple wire probe, which is really, really messy. Okay. And the size obviously goes up as you consider these probes. Okay. However, there are situations, all these may not be practical in the case of a boundary layer. The reason is this. Let's take a probe like this. This cross wire, right? A cross wire clearly is, as compared to a single wire which is going to be like this, a cross wire, when you do this, it turns out the length scale of the cross wire, the cross section is going to be larger, which means there's a question of how close I can go to the wall with a cross wire. Now this doesn't arise in the case of a jet or a wake when there's no wall. In the case of wall bounded flow, it matters. You can only make it so small, all these cross wires and so on. If you want to go very close to the wall, it's difficult. So sometimes we use a single slanted wire like this, right? And if there's a flow which comes like this, right? If I put it this, I can slant it like this. That would measure U plus V by root 2, let's say. And I invert it, it will become like this. I can measure U minus V by root 2, but not simultaneously. So if I want to measure at different heights, I am limited by spatial resolution. I can go for a single slanted wire like that, where I can really make it small. Move closer to the wall, put it like this, measure something like this, and go through a profile. And invert it. And then measure this, right? So if I now average this, you see, by combining this and this, I can get things like U square, V square, and UV. Okay. So it's easy to see why you can do that, because I can get things like U minus V square by root 2 square, average of this. Okay. I can also get U plus V whole square, it should become 2 perhaps. When I do an average, this is what I will get when I do the mean square value of that. by adding and subtracting these quantities, I'm sorry, I cannot get u square, v square separate. I can only get u square, v square together. U square plus v square. I cannot get u square and v square separately. And uv. By adding and subtracting this. We have used this successfully in flows like this. Okay. That's very useful. Okay. This is in fact a typical old-fashioned, simple-minded manual traverse, but you can also have all kinds of fancy traverses, which I will not go into the details of. Okay. Now comes a very interesting thing. If you are really interested in this Hotwire thing, I would urge you to at least have a look at this book by Tony Perry's book, Perry, Hotwire Anemometry. It's a Bible for Hotwire users. It's such a great book. It was written in the 70s, and I think it's really deep, very deep. Now there is this picture, if you want to understand. In one shot it explains many things. What is plotted here, this axis you have velocity square root. Here you have current square, right? So you can have very many trajectories of that, okay, where the resistance is 0, will correspond to a line. The different kinds of King's law are plotted, and this is of course the so-called, when R tends to infinity, it's a so-called burnout limit. Your resistance becomes so large that it gets burnt out. And typically, if you are using the so-called constant current anemometer, what is the thing about constant current anemometer? The current is kept, which is constant. It's very simple in terms of a circuit, right? The moment you have a voltage source, you connect it to some sort of a resistance and so on, it's easy to see how you can cook it up. Constant current trajectory. In this picture, it will amount to a traversing in this direction. It is indicated by C. Whereas if you want a constant temperature trajectory, you go along this line. It's easy to see why it should be so. It is this line which would correspond to constant resistance, right? So you can work it out yourself why this line, this slope is important for the constant temperature moment. Well, I must also tell you in the past 20 or 30, so constant current is the very first one, right? Constant temperature is something which came about a bit later, around 40s, 1940s and so, especially after we got all those fancy op-amps and so on, 50s and so on. That's when it really took the modern shape. Constant temperature is more common now. Constant current is used primarily for, if you are interested, as a cold wire circuit, especially if you are interested in measuring temperature fluctuations. It's not that constant current is useless. It is useful, but not for velocity, not for turbulence or velocity fluctuation. Now, there is something else which has come in more recent times. That's called a constant voltage anemometer, which is about 20, 30 years old. By some people, it was actually an Indian who started this company in the US. He has been talking about this constant voltage anemometer. He claims that that works beautifully in very high Mach number flows, of the order of few, especially hypersonic kind of Mach numbers. Well, I would not say anything more. But let's be very clear about the basic physics of how these work. Without going into any further details, maybe I'll come to that in a minute. So understand this plot. Different trajectories here correspond to different kinds of operation. Now a typical bridge, a typical constant current bridge will look like this. A voltage source, oops. Oh. A voltage source, you see that the resistance you want to measure is 1 ohm of a Wheatstone network. And then of course you can have an output voltage. And the key point here is that there is no feedback. What you get is what you get. So if the time constant of the sensor has changed, You can't do it. You cannot dynamically change that. For every operational condition, you have to change that. That's the problem here. However, if you have this constant temperature circuit, which is really this, which I won't go into the details, but the key point note here is that there's a feedback circuit there. There's a feedback circuit. As a result, it's able to correct its operational point, respond in terms of its adjusting its thing, adjusting its time constant dynamically. That's the key. Now, okay, this is, I would say, the master plot, I would say, of what Perry's book, in fact, I've taken this also from Perry's book. This is showing the intersection of what is known as the circuit equation, which has come from the electronics. Now what is that? Typically you would have, and of course the wire equation. Now the circuit equation, you can write the equation for by Kirchhoff's kind of voltage and current laws and so on. You can write for the voltage, right? That's the so-called, I won't go into the details of it unless you are interested, but point here is that we have lines like this. What is this showing? This is showing RW and this is I1, the current. On this plot, these kind of lines are what are known as the circuit equation, whereas a typical wire equation, which is no more than our King's law, old King's law, will look like this. The point of intersection of these is actually your typical operating point. It is in fact a very useful way of looking at why a hot wire functions the way it is. So I'm suggesting this for those of you, especially if you go to this limit, for instance, is the burnout limit. This limit corresponds to the U no velocity being there. Okay. Well, the circuit and wire equation are given here, which I will not go into. This has come by solving the circuit equation, and this is simply your simple form of your King's law. The second one, this double start thing, is the wire equation. Okay, this is perhaps one of the most important things about that. This is where the physics of the basic why hot wire works the way it does. Now people often make the statement that its constant temperature anemometer is the best there is, right? Not so the constant current, or certainly not the constant voltage. Now what is the idea behind that? The idea is that it's a very simple idea. It's to do with the idea of thermal inertia. With a constant temperature, what is it you are doing? You are changing not the temperature or resistance. You are not allowing it to change. The feedback will make it go back to the same thing, which means the temperature doesn't change. Whereas in a constant current anemometer, the temperature would change. Now, let's say the temperature has changed. You wanted to bring it back to a certain other condition. You can imagine how sluggish it is, right? The thermal process is a sluggish process because you know about already studied about diffusion of that. It's a very sluggish process indeed. So that's going to compromise your frequency response. That's why any process which involves changing the temperature is not going to be, to first order, not as good as keeping the temperature constant. You have thermal inertia to contend with. That's the key. If you remember this, everything else is straightforward. Okay, so let's now look at that. If you do the so-called simple static analysis of a circuit or any system, right? Typical first order systems, you would have studied this. Output input relation, they are related by the so-called sensitivity. What is it? It's simply the output by input. So if this is my velocity fluctuation, this is the voltage fluctuation, ratio is this. Now let's now talk about a constant current anemometer to start with. What is it? Simply a device where the current is kept a constant. Now it turns out the typical frequency response of that will go like this. Sensitivity, the sensitivity of that will go like this. What is sensitivity? How well the output is able to track the input. But it turns out it's as far as low frequencies are concerned, the output is, because low frequency is slow, the output is able to faithfully follow. When I put omega equals 0, S equals S naught. Output is able to faithfully follow the input. But as I keep increasing my frequency, higher frequency, fast moving things, clearly this is going to be different. There's a delay, right? As a result, if you plot now the sensitivity as a function of frequency, it's going to drop. This is S plotted here against omega, the frequency, in this fashion. Okay. Now, what is this M? M is obviously inverse of omega. It's a time scale. There's of course the so-called time constant of the wire, right? M is the time constant. It's typically of the order of 10 to the minus 3, 10 to the minus 4 second. That to first order decides your time constant of it's purely coming from the basic wire material and other properties. Now note that I can reduce my M. I want to, for it to be faster in terms of response, I want to reduce my M. The time constant has to be as small as possible. I can reduce it by changing the diameter of the wire, making it smaller. I do that because the thermal capacity is proportional to mass and hence the diameter, square of the diameter. So I make it smaller. Typically, if it's 5 micron tungsten wire, you want to improve that, you can always go for, let's say, 2.5 microns. 1 micron is the smallest you can manage, because you remember, it's not, people will sell you all these wires, tungsten wires, and say it's 1 micron, right? There's no guarantee it's going to be uniform, because the wire drawing technology may not be necessarily uniform, because we have seen that how it is done. In fact, we got many years ago lots and lots of, we went to one of those disused light bulb manufacturers, because they use tungsten there. We got them to make tungsten wires drawn out for us, and in fact they gave, I think it was almost an experimental basis 15 years ago, and of course we got lots and lots of, probably few kilometers of the wire for about 10,000 rupees or so, whereas if you had imported, it would be a king's ransom. But the point is, there's no guarantee that the wire diameter is a constant all through, especially if we make it very small. The drawing technology becomes more complicated as it becomes small. So there's a limit to what you can do. And secondly, the strength. It will break if you make it too thin. You can only make it so thin. Okay, so the key point here is that, so that is typically how a constant current anemometer responds, its frequency response, it drops. So typically, your omega naught in this case goes like 1 upon m, typically. So if you now want to improve this, what do? You can, if you know the time constant of that, if I can take the output and feed it to a circuit, an amplifier, which does the frequency response in this fashion now. This fashion, sorry. It amplifies lower frequencies by this amount. This is the gain, right? Higher frequencies in this fashion. In other words, I am trying to multiply by an amplifier which multiplies by something which is same as this denominator. It will cancel that nicely so that it will have a flat frequency response, right? That's what this amplifier behavior is. As a result, I will have a frequency response effectively like this, and that's precisely what you do in a constant temperature anemometer, right? You dynamically measure that, whatever is that, and then it's fed back, and then it compensates in that fashion. Now the constant voltage I told you about also does something similar, but I will not get into the details. So the compensating amplifier used in the output, you can use it either in the constant current or constant temperature, by the way. Except that in the case of constant current, I have to go and tweak the amplifier parameters. I have to give the input, right? Because the time constant keeps changing. Whereas the constant temperature, it is automatically done because it's a feedback circuit. But it's a very complicated circuit, okay? Right, let's now get down to business. Typical measurements of typical measurements from boundary layers, right? It will also amplify some of the points I made, right, about the wire length and so on. What should be the typical active length and so on. Okay, this is a typical measurement of a log law, right, in a zero pressure gradient turbulence boundary layer. So this axis is, of course, this y plus, the wall units. This is a u plus. And what is compared here is the standard log law which you find in textbooks. And what you see here is this region where you see. What is compared here is with a pitot, with a hot wire, with a cross wire. Now you can measure the cross wire, even a U or V component separately, of course. Told you, it's straightforward, and I think Sendil also mentioned this in the morning. And you should be able to reproduce this no matter what you do, right? That's, of course, the main thing. Note that there are not that many points when you get close to 10 or so, y plus equals 10. Okay? Because that's the problem with boundary layer, you cannot get very close to the wall. I must say, in recent times they have developed something called the so-called nano probes and so on in Princeton, where they say that they are able to go very close to the wall, right? I don't know of many other groups which have done that. They have got very high Reynolds number flows, what is known as a super pipe and so on. Okay, let's look at a typical measurement of U prime square. This is a very important thing, for both from turbulence research as well as the turbulence physics, which is the turbulence intensity. Now I must say that this has been the heart of many controversies in the turbulence literature. For example, notice that this U prime square, which is the RMS, the mean square velocity fluctuation, normalized by the friction velocity square, which is non-dimensional quantity, typically it reaches a value of 810, right? Now if you plot it, And these are different experiments. There is this inverted triangle which you can see some of that, that's from LDV from Stanford. Whereas note that the circles, I'll come to the circle. Circle is measured with a single Hotwire. It's called single Hotwire is HV. CW is for crosswire. ZPG2 is a different Reynolds number. Two different Reynolds numbers are plotted, and corresponding value from the LDV. First of all, note that there's something called, of course, there is a variation of Reynolds number. Let's ignore that for a moment. Look at this something called L plus. That's very important in the case of a case of a boundary layer or wall bounded flow. What is it? When you go very close to the wall, remember, typically, if you can imagine a boundary layer like this, right? Profile like this. Typically, if you go close to the wall, the eddies are going to be very small, typically. And as you go away from the wall, they are larger and larger. So sometimes people model these as these sort of structures. It's very small. This length scale is here. As you move away, is as large as the distance. So typically, when you use the so-called mixing length kind of model, right? L equals kappa y, what you're really saying is that as I move away from the distance, the typical size of this, you can take it as the size of the eddy. It goes almost linearly. That's only true, of course, close to the wall, the log region, but that's certainly, it conveys the idea. So when you go very close to the wall, what this says is that I can expect the eddies to be very small indeed. Now what will happen now, imagine your hot wire is a certain size, right? Active length of the hot wire is this much. It's going to do an average over this length. Imagine if I'm going to, my eddy is larger than my eddy, it's obviously going to smear it out. It will not give a faithful representation of what is contained in that. As a result, you expect, especially when you go close to the wall, you expect your active length of the wire, if it's a Wollaston wire or a tungsten wire, is the full length itself, to be reasonably small. How small? Well, there is a slide which says how much it should be. I think he has put it here, I think the summary, somewhere here. So it should be L, the length of the active length of the wire, normalized by U tau, and the viscosity should be less than or equal to 20 to be able to capture that. If you get larger than 20, you don't expect to capture the small eddies near the wall. There will be attenuation, and that's precisely what you are seeing here. When you look at, you see that when L plus is equal to 40, you see that it's somewhere here. As you go make it with about 23, to go closer to that, you got there. Now this is measured with the LDV. In LDV you don't have that problem. You have different problems with LDV, but not this problem. You can always make it a point, right? You see there are other, which I will not show here. LDV has problems with V square and so on. So that brings us to the idea of the active length of the wire. So the broad thinking is that my hot wire should be, now on the one hand we say that there is a requirement, if this is the diameter of the wire is D, L is the length of the wire between the prongs, you want your L by D to be of the order of 200. If you make it smaller than that from this requirement, you will have heat transfer from the ends, completely frustrating your measurements. So on the one hand we say your length should be at least 200 times the diameter. For the same reason, if you try to, you should also, you have a conflicting requirement here. When you go close to the wall, it should also be, the L plus should be less than 20. You want to capture that, otherwise you will not capture that. Okay, so now this is UV, this is mainly from the crosswire. You can again see the comparison of the crosswire with your LDV. You see that is there because the Reynolds number changes, but look at how it stops here. You don't quite capture the region, right? That's mainly because you can only go that close to the, with hot fill closer to the wall. You cannot get closer than that. Okay. Now these are the so-called IR moments, which if you are interested in finding out, the energy balance, the kinetic energy balance. There are different terms, right? Production, dissipation, diffusion, so on. You cannot of course measure all these. You can only measure some of these. Example, it's impossible, I think, to measure pressure fluctuations, correlation of pressure with velocity and so on, right? In any flow, that's true, it's hard. But you can measure some of those things. If you measure those, typically they will look like this for different flows. I just wanted to show that it can be done. I am not going to the details. But the point here is that something like V cubed, the vertical velocity cube, the typical error there can be, I think I put it here somewhere as a slide. Some of the errors are given. Reynolds shear stress you can actually do reasonably well, 5 to 10%. With all these micro probes you can even do better. But look at the triple product U cube, it's 3 to 5, that's okay. V cube 70 to 80%. Why is that? V is always going to be difficult because V is so small, the velocity, vertical velocity is so. Now, it's a very favorite question of some of us. If you ask the students, which is difficult to measure, 1 meter per second or 100 meter per second? Forget about all this. What do you think? Which is more difficult to measure? Is it 1 meter per second or 100 meter per second flow? Why is that? Sorry? No, that's a detail. That's a detail. You're right, it's a 1 meter, because some people look at the large number and say that's more difficult. It's not. Very simple, because the fluctuations are so large as a percentage, errors are enormous. Exactly. Okay. So that's broadly speaking the idea. So as you go for smaller and smaller values, you have to be extraordinarily careful. You should in fact take it with a pinch of salt, some of these measurements. Okay. So typically it is this. So there is this very nice paper in these experiments and fluids by Benedict and Gold, which gives you some other techniques. Usual measurements make use of Gaussian processes. This uses something else. If you are interested, you can look up that. How a detailed analysis can be made of error and so on. It's there. It's in the thesis of this guy Dikshit. He has given all this. Okay. So let's now look at some other results. Oh, okay. A typical cross correlation. So now the other, you can do all kinds of other things. I can in fact to put a probe at one location near the wall, one other from the wall, and then ask how well these are correlated. For example, if I told you a boundary layer looks like this, the eddies in a boundary layer look like this, an average sense. What does it mean? How do you get pictures like this? People put a probe closer to the wall, move one other probe at different locations, Hotwire probe, and take these correlations, cross correlations. It's cross correlation because it's not the signal with itself. It's a signal with something else. Except that it is a space correlation. These are two probes separated in space, and then I can take a correlation. So typical methods are given here. Maybe I will, if there is a specific interest, I'll go through that. Otherwise, I'll just skip that. Typically, it will look like this. Typical numbers. Let's look at typical numbers with Hotwire. What kinds of frequencies involved and so on. These are primarily accelerating flows. What I am talking about here. I am talking about two different kinds of bound layers. One is zero pressure gradient bound layers, which means that as I go along the flow, I don't expect the flow to evolve because the free stream velocity is a constant. Whereas this accelerating flow, in all these which I have listed as PG, are pressure gradient flows, where the velocity accelerates in some fashion, and you can see the typical numbers which are involved there. The typical speeds are about 16 to all the way to a very low speed about 2.8 at a reference location that's being accelerated. Now, there are two aspects here. For sampling theorem demands, you have to sample at 2 times if you are interested in capturing a particular frequency, you have to do at least 2 times that. But don't do just 2. Maybe do 3 or 4. 4 should be okay, usually speaking. So if you want to capture Kolmogorov scale, clearly you can work out different ways of doing that. None the most obvious, but let's look at the Kolmogorov scale here. typical numbers you can see here. The Kolmogorov scale for some of these, about 3 kilohertz, all the way to 0.08. Why is it so low? Because the velocity itself is low and is also an accelerating flow. The low Reynolds number flow. In low Reynolds, this is a Reynolds number which makes those frequencies, if we go for very high Reynolds number flows, those frequencies of the Kolmogorov scale really become very, very large. Okay, but these are relatively low Reynolds number flows. You see that it's about 3 kilohertz. So if I sample at about 10 kilohertz, which is what is done here, that's good enough. You can in fact ensure that that's reasonable. Whereas here you see 0.08, it's done about 3 kilohertz. It's changing. All right. Now the more important thing is that the other question is that, so that part is obvious. So-called sampling theorem tells me I have to sample at least twice that frequency, because you take it through the so-called analog to digital card and acquire that. But you must remember there is a issue here. This is something which I was talking to Senthil about in the morning. If there is something called the aliasing error, right? What is an aliasing error? Okay, I think it's best explained with what I think the picture which I think TS drew in the morning, that's also probably a good one. So if you have a sine wave like this, if I am going to sample at only frequencies like this, what is it I am doing? I am trying to sample an event which has this time scale, fast time scale, with something which is a lot slower. Right? Obviously, I am not going to capture that. I will get spurious frequencies here, which is not there in the original signal. Okay, you can have variants of this. But I think it's vividly seen. This is also sometimes referred to very colorfully in signal processing as the wagon wheel effect. Now what is it? Wagon wheel effect refers to, if you have seen all, especially the old movies, right, Hollywood movies and so on, movies like Ben-Hur, right, the classic Charles Heston movie. It was very well known for a chariot race at the end of that. The grand scene where 1950s vintage. What would you see? Or even the cars with the wheels rotating, right? You will see the wheels rotating backwards. Now what's happening is that the cameras which are capturing, what is the typical video camera's frequency? It's about 40 milliseconds. 24 frames per second typically, right? 24 or 25, that's about 40 millisecond spacing. If you try to capture something faster than that with this, obviously, you might have seen sometimes when you watch TV in a relatively dark room, you would see that in that reflected light of the TV. That's like a stroboscope, right? The light keeps changing. The fan, you may see it going backwards at lower frequency. That's also exactly this. It's called wagon wheel effect. What it means is that what is actually a high frequency event showing up as a component, a lower frequency component, that is referred to as aliasing. So this is in fact a problem which comes from sampling. So it comes from sampling before it goes to your ADC. What you should do is that you should cut out all those annoying IF frequencies beyond what you are interested in. Completely cut it out with a low pass filter. You have to do that at that stage. Then of course when you sample it, acquire it, you will avoid that problem. You have to necessarily do that. Okay. That is of course as far as then low pass filter it, maybe amplify it and then acquire it. Okay. And then you have to do this usual ADC thing, like whether you use a 16-bit ADC or you can also use the fancy 24-bit ADCs that just come about and so on. But that's anyway, that's not going to help a great deal. You have to also do all kinds of other things like massaging the noise. That's a nightmare. That's where digital filtering could be useful. The other noise, right? For example, there is a noise which comes because of, there's a broadband noise which comes. See, aliasing is only noise which is coming from higher frequency lower, which you can cut it out with a low pass frequency, low pass filter, which allows only the lower frequencies than that. But there are other frequencies, other sources of noise, right, which come from other things like electromagnetic interference and so on. For example, if you have a switching circuit, like a motor operating there in the neighborhood, that could in fact corrupt that. You might have seen this, right, in all these computers and so on, they give this sort of beats to avoid that so-called EMI, electromagnetic interference. If it comes, it's a nightmare to avoid that. It's not obvious one way or the other, one way is best. Sometimes people may have to even use something called the Faraday cage to avoid that interference. Okay, there is other consideration about this frequency. How long should the signal be? Short is of course fine. If you make it, you have to really make it short enough, fast enough, so that I can capture those, that's okay. But what should be the length of the signal? How long should I acquire the signal? If you acquire it for t, it turns out this 1 by t will decide the lowest frequency in your time series. Not only is the lowest frequency, it also tells you about 0 is of course the first. The next one is 1 by t. Next one is 2 by t and so on. If we call this as delta f, this delta f, 2 delta f and so on. So your smallest, the spacing, the resolution of frequency in the spectrum will be decided by the length of the time series. You have to really make it large so that you capture as small frequency as possible which is contained there. And in fact, you have to typically you do it in terms of so-called eddy turnover times. How many eddy turnover times? So that time scale, you multiply this something like t into u by delta, for instance, a length scale. You in fact do something like this, so that there's an expectation about so many structures crossing that. I typically do it of the order of tens of thousands typically. Some of the spectrum, if you really want the controversial spectrum I told you about k minus 1, right? Typically I ask people to do it for about, my students, I tell them at least 1.5 to 2 minutes minimum. I know some Australians who do this, who do boundary layer measurements, who have in a tunnel, which is overkill. Actually they do it for 45 minutes. The conditions might also change, but I think that's madness. Anyway, this should be very large indeed if you want to get a nice average. Okay? So you can get plots like this, you see. A typical correlation plot will look like this. Okay, the other point is about Taylor's hypothesis. I'll come to in a minute. So typically you plot this axis, this is x and this is y, and what you plot here are the correlation which is defined by this. Tau x naught, which is the wall, there's one sensor at the wall at a given location, and then u, velocity somewhere else. So your wall shear stress sensor, velocity sensor somewhere away from the wall with a time delay, normalizes in this fashion. That's what is plotted here. So if you connect all these, I'll probably, the procedure is all, I not explained here, you get contours like this. So it will give you structures which are leaning like this, you see. So it is an indication of the sort of eddying activity, large eddies especially. Remember, these correlations are primarily a signature of large eddies, relatively large eddies. Okay, and I can do this sort of cross correlation plots. Okay, now this is about spectrum. I told you about this very controversial thing. I must say that is one of those elusive things in the literature, which so what is plotted here is what is known as the accelerating boundary layer flow. We are exploring under what conditions you will get this k minus 1 spectrum. This phi 11 is the spectral quantity which is plotted, and if I integrate this, I will get the kinetic energy. What I called as E earlier, we use the symbol phi 11 here. Okay, it's the spatial spectrum. Now, how do you go to spatial spectrum? You get, of course, a time series. From time to space, how do you go? You assume, of course, make this so-called Taylor's hypothesis. Now, what is the physical content of Taylor's hypothesis? Let's be very clear about it so that you don't use it where it's inappropriate. So, if you now look at the advection operator, you can write it as d dx plus u d dt, u d dt, operating on whatever is 0, any average quantity. This is essentially the assumption. What does it mean? The advection operator, as you go along a streamline, for instance, is such that this quantity does not change by and large, it's frozen. Now for this to be frozen, when can I expect that? This operator should be like this, d dt equals minus u d dt dx, d dt equals d dx. Or it's like x equals ut. Now what is this u? That's of course a controversial thing as well. It could be the local velocity, mean velocity itself in the flow, for instance. So you can imagine this is the speed with which the eddies are convected in the flow. Essentially what you can do is your time series, what you got, you can convert it to a space series by the simple trick, t equals x by u. Okay, and you can, why is that important? Because you are interested in the Kolmogorov theory and all that. It predicts the spectrum in terms of k, which is about space, whereas what you are measuring with the Hotwire is the time. That's why you need to do that. On the other hand, if you have a PIV shot, right, let's say instantaneously, you don't need to do all that. You directly get your k, right, if your picture is fine enough, I mean broad enough, it is detailed enough. One shot, instantaneous picture of a PIV, I will get my space series, right, velocity at different points I will know in one shot. Okay. In fact, if you are using a PIV, if you want the temporal data, you have to do an inverse kind of Taylor's hypothesis. You have to use this to come back to space, I mean time to space and so on. Now, Taylor's hypothesis obviously is only a hypothesis, but it's remarkably it works in a variety of situations. People have verified that. Okay. Now, when will it obviously, if you have a fluid element or parcel like this at time t equals 0, x equals 0, Taylor's hypothesis means it's a rigid convection, which means a parcel pretty much stays this way. It doesn't evolve a great deal. So, if it evolves a great deal, it will look like this. What does it mean? Typically, one measure of that is a rigid convection. So, you would expect the correlations and so on to stay put. So, the correlation decays. This is a good idea of. So, clearly, when the fluctuation levels are very large and so on, there is a lot of buffeting which goes on, which can upset the Taylor's hypothesis assumptions. But by and large, it's quite robust, I must say. Okay, and these are other fancy things we can do with this, which I will not go into. Correlation length scales and what is known as a Vita technique and all that. It's just to show the power of all this, what you can do with Hotwire. Many more things you can do. So important duration to summarize are, I'll just take a few more minutes. I think I've got 8 more minutes. The sample duration is this is the key, TU infinity by non-dimensional time of acquisition of data. That should be very large. As I said, typically 20,000 or 30,000. I think it's there in one of the plots earlier. I think the how many eddy turnover times. Oh, it's not working, is it? So I don't know if it has. No, it doesn't have in terms of eddy turnover times. It's about 20 to 30,000 times. You can in fact check all that here, but the second thing is the spatial resolution of the Hotwire needs to be very small. Third thing which I did not mention about is the temporal resolution. In terms of time, if I want to capture the so very small time scales, right? Just as I talked about the L plus effect, that delta t should be such that delta t u square by nu should be less than or equal to 3 if I want to really resolve up to the dissipative scales. This is not something which is often thought about carefully. I think it's because you really want to capture up to dissipative scales, it is this. Oh, incidentally, I must tell you that there is this thumb rule. Let's say you don't know anything about a flow in terms of Kolmogorov length scale or whatever. There is in fact a thumb rule which is often used. I think it came from atmospheric people who were making all kinds of bound layer measurements. There's a thumb rule which seems to work very well for most of the practical purposes. If your speed, don't ask me the source, I cannot remember where it is, but we have found it to be very useful. You know the speed of the flow u in meters per second. You multiply this by 300, right? Take this roughly as your Nyquist frequency. Okay, so you have to multiply this 3 or 4 times to be able to sample, and it actually works reasonably well, especially for a range of velocities. Okay, so it's something which must have evolved from the empirical thing. I think it comes from people like, I don't know whether it's Bradshaw or Wingard. I think one of these, I've forgotten what it is. So this is something which, especially if you want to capture, especially most of the energy containing scales, it does a good job of that. Okay, this we have seen. The other things which okay, wall jet. I will be very brief about this. Wall jet is, as I said, a marriage of both a jet and a boundary layer. So if I take my hand here, if I blow it's a jet, right? If I blow it's a wall jet. There's a wall with a jet on one side. Jet is being modified by the wall. So it has this kind of profile. It's important variety of film cooling applications and so on, right? We can imagine all kinds of cooling application. There is a wall over which there's a flow which tries to cool that. And this is of course like what you have in the so-called Konda effect. In the flow control kind of problems, there's something blown on the surface and so on. You have a velocity profile like this. Fluid dynamically it's important because it's interesting because there is a region there where there is what is known as a counter gradient diffusion region. In other words, there's a region where there is negative eddy viscosity. Physically what it means is eddy viscosity is thought to be positive, right? There's a region where in effect it's like a negative eddy viscosity region. But I will not, this is not about wall jet physics, it's more about the measurement. Let's do that. So the reason I mentioned this was because here we found it very useful to measure. Yeah, this is a picture of the outline of the wall jet on a top view on the surface. It's developing on the surface. There's a flat plate on which it's developing. And that's the, okay. Now you zoomed, really zoomed view. Yeah, even the solder tip you can see. Yeah, this is you're also using Wollaston, platinum rhodium thing, because that's what matters for active length. Okay, typical wall jet velocity with a measured with hot wire, you can see that. Okay, now it's interesting here because if you look at the flow, visualize the hot wire, the forward region of the hot wire, the wall jet, the eddies would lean like in a boundary layer. Outer region, it would lean backward like in a jet. In a jet, the eddies would look like this, the flow visualization. Now, we thought, you asked ourselves, can we capture this with the 2-point correlation with hot wire? Right? In the case of a curved wall jet, it's even more dramatic. It's leaning backward so much, you see. You can see that. The curved surface on which you have a jet which is going, which is a wall jet, curved wall jet. You see that it leans backward even more dramatically. So, if we do a 2-point correlation of this, how does it look? Well, this is a spectrum, of course, measured spectrum, which is a very peculiar case. It's not like whatever you saw in the case of boundary layers. It's also what is known as a pre-multiplied spectrum, by the way, where you multiply typically by this k wave number, which is the same axis as here, for reasons I will not go into. Even the previous spectrum, what you saw, was a pre-multiplied spectrum. Spectra are sometimes plotted in what are known as the compensated plots, so that you can see some regions better. I will not get into the details here. So these are typical spectrum. So this is again the largest eddies, the smallest eddies in a pre-multiplied fashion. Okay, now this is where we use the slanted hot wire because we wanted to measure the Reynolds shear stress. Okay, if you look at the Reynolds shear stress, you see that at different locations how it's changing. Now in this flow, obviously going closer to the wall with the conventional cross wire would have been impossible. This is the utility, for instance, of the 2-point correlation, spatial correlation. So it gives you the idea of the impression, the time averaged impression of what the eddy shape will look like, which is in conformity with what you saw in the flow visualization. Forward leaning, backward leaning, like in flow visualization. That's it, is it? Yes, probably that. Okay, I think that's about it. And I just wanted to say one last point. If you want to measure very low velocities, you could do that, very low velocities, dot wire. One trick is what you could use it as, it's not that this, you could introduce, for example, there's a flow with a very low velocity, let's say, half meter per second. Most of the traditional methods, there's going to be a problem because even if you put hot wire, how do you independently measure that? There's a problem, even calibrating that. So one of the ways in which you could use the hot wire is very interesting. You put a cylinder, right? A cross flow over the cylinder will lead to the Kármán vortex shedding. You could put your hot wire here and measure the time series, right? Measure the time series here. And there is a very nice correlation between the you can measure the frequency of this time series. If that frequency is f, and if you non-dimensionalize this by this, there is a very nice correlation relating it to the velocity, function of velocity, Reynolds number and so on. Very well known, okay. So you can, by measuring the frequency, you can immediately find the Reynolds number and the velocity. That's how you could use, but very low velocities, you want to measure it successfully using hot wire, use what is known as a vortex meter. This just a cylinder, vortex shedding behind that, measure its, put the hot wire here, get its frequency, and from there you can use a correlation to get the velocity. Okay, that's just as an aside. Are there any questions here?
Actually obvious because of there is no velocity in other friends, the other region, so hence it's happening.
Where no velocity where?
It's outside the region what we are considering, means we are doing very close to Earth, so there is no velocity out of the
Yes.
So backwarding happens anyhow.
See, I just showed that here, the limited point here is that how do you get it with a hot wire? Conceptually, there are other issues I'm not going to. It's not about the physics of wall jet. The physics of wall jet would be to use that structure to explain why there is a counter gradient. That's not the point here, right? Here, how do you successfully use hot wire? Because this meeting is about hot wire. Any other question? No. No. You can do ideally in situ calibration you could do, but no, in general I don't see any. Well, there are always finer, see it depends on what you want. If you are looking at first order quantities, you see, we have of course measured things in jets too also, okay, but I have not talked about it. People have lots of measurements in wakes and so on. Yes. That's what I'm saying. In some sense, there's a worst case scenario, right? You can actually, wire mortality is more for one thing. Other than, of course, if you go close to the wall, you know what would happen? There's extra conduction to the wall. There's a violation away from King's law already. So there are all kinds of effects like this. So in that sense, your flow is a lot more benign. It's friendlier, right? The bound layer is a nightmare. Especially some of these adverse pressure gradient bound layers can be terrible. Favorable, this is a favorable pressure gradient bound layer, I talked about some of that. There the problem is things change very rapidly with streamwise distance. It's not even obvious if you can use Taylor's hypothesis because things change. But it turns out you can use it. We have, of course, you can verify that, the ways of checking that. So you would have thought it's an evolving flow. Taylor's hypothesis should not work. It does work. But yes, you're right. Hot wire measurement in bound layers in some sense is the worst case scenario. If you have also a rough wall, it's a double whammy, as Americans say. You can easily break your hot wire. Other questions? Thank you then.
We all thank Professor Ramesh. He has spent so much time here. He has come morning by 10 o'clock and he's staying here. So let us appreciate him by just